doing? Hold on, let me put this away. My computer restarted it itself, so it took me a little longer to get here. Sorry about that. Glad to see that you're here. Let me open up the gallery so I can see everybody. Okay, yay, look at all these people. Let's see, I don't have any announcements, but I'm willing to answer some questions. Does anybody have any questions they want to ask? It's all blurry. Nope. Okay, hold on a second. Let me see if I can get it to not be blurry. Where did it go? Okay, there's one. Okay, so today is the day that we've all been waiting for. So, you've heard the rumors, that Taylor series are part of this class, and you've probably been misinformed that they suck. But you know what? They don't suck. They're awesome. And today's the big day that we get to find that out. And so that's why we've got like glittery backdrop in celebration. Okay, so let's learn a little bit about some. Let me get this up. Let's learn a little bit about Taylor series, and you will see what all the excitement is about. All right, there we go. So, we're in section 8.7, Taylor and Maclaurin series. Wait, I don't know if I have the volume up, do I? Oh, I didn't have the volume up. Maybe somebody said something, I didn't even hear you. So if you said something, we say it again. Okay, I didn't miss anybody. Okay, good. Okay, so 8.7, Taylor and Maclaurin series. Okay, so here's what our goal was. Given a function, how can you find a power series that represents that function? So goal, I'll put that in yellow, goal. Given a function, f, find and a location A, let's just say. What we want to do is we want to find a power series that gives the same value that f does near that location. Okay, so that's the point of this section, is how do you find such a power series? And we made a lot of progress. We made a little bit of progress, I should say, last time. And we made enough progress that Diego was able to go, yeah, I see how the rest of this is going to go. So maybe some of you haven't had that stroke of insight yet. That's okay. We'll do all the steps until you do. So, so where were we? So here's finding that power series. Well, we know that, a power series, we know what a power series looks like. So a power series f of x, if it's a power series, it looks like something like n equals 0 to infinity. We've got some constants, and then we've got x minus a to the nth power. It's a bunch of powers of x minus a. And if you don't like it that way, we can also sort of represent it as this. C0 plus C1 times x minus a plus C2 times x minus a squared plus C3 times x minus a cubed. And I think I'm going to pull that, line it up this way, so there's more room to put more steps. Plus C4 times x minus a to the fourth plus C5 times x minus a to the fifth, and so on and so on. Okay, so this is just a polynomial. And I mentioned this before, but I'm going to say it again this time. Everything there is fixed except for the coefficients. So A is the location that we're trying, it's the X value that we're trying to find out what power series works. So we have to leave A just to say we're not plugging in anything there. X is the variable that has to stay. N is the counter. The only thing that there is to find, I mean, not the only thing, because there's infinitely many, I get it, but the point is we should focus our attention on the constants, on the coefficients. So these are the things that we care about. So finding the power series means find these coefficients. So what I'm about to do for the next 5 minutes will be finding the coefficients, and then we'll know exactly what power series represents a function. So we're going to try to find these coefficients. And okay, so I'll just leave it yellow. Finding these coefficients will give us the power series. That's all we have to do. Okay, so we had a bunch of steps already. I'm going to do them again because this is a really important part of class, and I just want to be sure that everybody sees all the pieces of it. So it's okay if we do a couple steps over again. How could we find C0? Well, the trick is we're gonna plug in some values, and just about any value that we plug in that's not A, we have some series. It's going to be hard to find the value if we even can find the value. But if we plug in A, all this infinitely many stuff goes away. So that's kind of the strategy. So we're sort of going to go back and forth. So the first thing we're going to do is, now let's keep that as yellow. Okay, first thing that we're going to do is just plug in A into f of x. Let me just say x equals A. Okay, on the left-hand side, I'm going to get f of A. On the right-hand side, I'm going to get C0 plus C1 times 0 plus C2 times 0 plus C3 times 0. All those guys are 0. X minus A is 0, so square it 0, cube it 0. So it's just C0. And the good news from that is now we know what C0 is. C0 is F evaluated at A. Okay, so we got one of them down. We figured this one out. Now the brilliant insight that that it must have been Taylor had to go forward here to find the other coefficients, well, what if we take the derivative? We remember from the theorem from last section that we can take the derivative of a power series term by term, and it works. So let's just do that. So take the derivative. And get f prime of x. Okay, so on the left-hand side, you just have f prime of x. And what happens here? Well, when I take the derivative, this constant goes away. And then here I've got constant times derivative of this. Well, the derivative of this is just 1, so I'm going to have C1. And I'm going to have C2 times the derivative of this, 2 times this thing to the 1 power, etc. I'm just using the power rule over and over. So the C0 goes to 0, and I'm going to have a C1 times 1, and then a C2 times 2x minus a to the 1 power, and a C3 times 3x minus a squared. All right, any faces to look at? Oh, there's Diego Smith. Okay, this makes me happy. Okay, so plus C4 times 4x minus a cubed oops. And then, C5, let's put that one in there too if we can fit it. C5 times x minus a to the, times 5x minus a to the 4th. And then, more terms, infinitely many more terms. We're not going to write them all down. Now that we've done that, we can do the same thing we did before. We can plug in A. When we do, this goes away, this, all the rest of these things go away again. And we're just left with the constant term. So plug in A, plug in X equals A, now to F prime. So F prime at A is C1 times 1 plus 0 plus 0 plus 0 plus 0 all the way down the line. So that's just C1. So now we know what C1 is as well. C1 is F prime of A. You might want all the coefficients to just be the derivatives, and that would be super cool. It's a little bit more complicated than that, but not a lot more complicated than that. Okay, so let's just keep doing the same thing. Take another derivative. Let's take the derivative F double prime of X. Okay, so we're looking at this line right here. I'm going to take the derivative of this line. So F double prime of X. Well, when we do, this is a constant, that goes away to 0. This is going to be C2 times 2 times the derivative of this thing. Derivative of this thing is 1. So I've got C2 times 2 times 1. What happens here? Well, I'm going to have C3 times 3. Then when I take the derivative of this piece, I'm going to have 2 times that thing to the 1 power using the chain rule. So it's going to be times 2x minus a to the 1 power. And then we're just going to keep doing the same thing. It's going to be C4 times 3 x minus a squared plus C5 times 4 x minus a cubed plus etc. On down the line. Hope you can see what I'm going to do next. Can you tell what I'm going to do next? Yeah, we're going to plug in A. We're just going to keep
plug in A.
Yeah, thanks, Nate. We're just going to plug in A and keep cycling through. So let's plug in X equals A now to F double prime. Okay, here's F double prime. So F double prime of A is C2 times 2 times 1, I guess we could say, plus everybody else is 0. So that's just going to be 2C2. So, okay, so C2 isn't F prime of A, but it's close. C2 is, is F double prime of A divided by 2. Okay, let's just keep doing steps until we see exactly what it's going to be. So another derivative. F triple prime. All right, so F triple prime of X is, okay, just as before, the constant term, this thing goes away. Now I've got a C3 times 2, derivative of that is 1. And then for this term, I have C4 times 3 times the derivative of this, which is 2 times x minus a to the 1 power. And then the next one's going to be C5 times 4 times 3 x minus a squared. And if we did another term, it would be, can I fit it in? Next one would be plus C6 times 5 times 4 x minus a cubed. And then there's, some more stuff. Let's put all this together. Okay, so same old thing, plug in a. To the third derivative. So f triple prime at a, that's going to be C3 times 3 times 2 times 1, plus, just like before, everybody else is 0. 0, 0, all a bunch of zeros. So that's going to be C3 times 3 times 2 times 1. You might be looking at that and saying, that's 6, Dr. Office. Why are you writing it 3 times 2 times 1? The reason I am is because we're going to see the pattern better if I leave it factored out rather than multiplying it together. Okay, so let's just roll with it. So now this means that C3 is f triple prime at a divided by 3 times 2 times 1. I'm going to do one more step. And I think from there, maybe we're going to be able to see what the pattern is, if you don't see it already. So we're going to take another derivative. F fourth derivative. Well, you know, sometimes people will write the 4 in parentheses. I don't know if you knew this, but it can get kind of crazy. If you want the 10th derivative, you know, you don't do something like 1, 2, 3, 4. You don't do this kind of thing. It'll just get crazy. You just put the number up in the as parentheses with the exponent means that's the 4th derivative. Okay, so how are we going to take this derivative? F fourth of x is, that guy goes away. Maybe it's hard to tell. Here's the separations between the terms. Okay, so the constant term goes away as usual. And now I'm going to get C4 times 4 times 3 times 2 times 1. Derivative of x minus a is 1. Plus C5 times 5 times 4 times 3 times 2 x minus a. Plus C6 times 6 times 5 times 4 times 3 x minus a squared, and some more stuff. What are we building up here? What are these, you know, we've got these C1, C4, C5, whatever, but this other piece, what is this that we're building up as we keep
like a summutation?
It's say that again, Zane?
It's like a summutation.
It's like a sum. Yeah, well, it's like a sum, but what's the name of, yeah, so we're definitely making a sum. I don't know what a summutation is. Maybe that's a word that I haven't heard before.
The thing with the exclamation mark, whatever that's called.
Oh yeah, that's exactly right. Factorial. That's exactly what we're building up, is factorial. And you can see where all these pieces came from, right? First we had to the 5th power, and then when we pulled that 5 down, we had to the 4th power, and then we pulled that 4 down, we had to the 3rd power, and we pulled the 3 down, we had to the 2nd power, and we pulled the 2 down. But you can see the factorial building. Yeah, so exactly right. So you know, we'll do this last piece, plug in x equals a to the 4th derivative. And it's going to be f to the 4th derivative at a is C4 times 4 times 3 times 2 times 1 plus a bunch of zeros. So that means C4 is the 4th derivative at a divided by 4 factorial. This one I can think of as the 3rd derivative of a divided by 3 factorial. All of these are like that. Look, this is the 2nd derivative of a divided by 2 factorial. 2 factorial is just 2. Okay, 2 factorial is a weird way to say 2, but if I'm trying to show you that they all follow the same pattern. Okay, this is f prime of a over 1 factorial. 1 factorial is just 1. Maybe you're worried about this. This is no derivatives, just f of a. You might be like, oh, we can't do that. But you know what? 0 factorial is defined to be 1. In some sense, 0 factorial doesn't have any meaning at all. But in order to make formulas look kind of nice, we just say 0 factorial is 1, and then it all works together. Yeah, Diego. you have a question, Diego?
I had an idea.
Okay.
Hello?
Oh, gosh, it says my internet connection's unstable. Sorry, but I'm losing everybody. Oh, no. What do I do? Let me see who I'm on. Okay, is my internet back? Can you hear me again? Uh-oh, what internet?